Hey Space Frontiersmen, welcome back to our channel, where we dive deep into the cosmos and explore the latest in space, science, and technology. The story of our universe begins with an event known as the Big Bang. This isn't just a theory, it's the most widely accepted explanation for how the universe began. But what exactly is the Big Bang, and how did it lead to the creation of everything we see around us today? Before we go into our explanation, we have a very small request. If you like our content, please support us by subscribing to our channel. It's a small click for you, but for us, it means a lot. Thank you. Let's begin. To understand the Big Bang, we need to go back approximately 13.8 billion years. At that time, the universe was incredibly small, dense, and hot. In fact, it was so dense that all the matter and energy that make up our universe were compressed into a single point, often referred to as a singularity. This singularity contained all the mass and energy that would eventually form galaxies, stars, planets, and everything else. Then, in a fraction of a second, this singularity began to expand. This expansion was not like an explosion in the traditional sense, where matter is flung outward into empty space. Instead, space itself was expanding, carrying matter and energy with it. This is the essence of the Big Bang. As the universe expanded, it began to cool. Within the first few minutes, the temperature dropped enough for protons and neutrons to combine and form the nuclei of simple elements like hydrogen and helium. This period is known as nucleosynthesis. However, it would take another 380,000 years for the universe to cool enough for electrons to combine with these nuclei to form neutral atoms. This era is known as recombination. During recombination, the universe became transparent to light for the first time. The photons that were released during this period are still detectable today as the cosmic microwave background radiation, or CMB. The CMB is a faint glow that fills the universe and provides us with a snapshot of the universe when it was just 380,000 years old. It is one of the most compelling pieces of evidence supporting the Big Bang theory. But the story doesn't end there. After recombination, the universe entered a period known as the Dark Ages. During this time, there were no stars or galaxies, just a vast expanse of neutral hydrogen gas. This period lasted for about 100 million years until the first stars began to form. These first stars were massive and short-lived, and their formation marked the end of the Dark Ages and the beginning of the epoch of ionization. The light from these first stars began to ionize the surrounding hydrogen gas, making the universe transparent to ultraviolet light. This process of reionization continued as more and more stars and galaxies formed, eventually leading to the universe we see today. The formation of stars and galaxies is a complex process driven by gravity. As regions of gas and dust collapsed under their own gravity, they formed dense clumps that eventually ignited nuclear fusion, creating stars. These stars grouped together to form galaxies, and galaxies clustered together to form larger structures like galaxy clusters and superclusters. One of the most fascinating aspects of the Big Bang theory is that it not only explains the origin of the universe, but also its large-scale structure. Observations of the distribution of galaxies and the CMB show that the universe is homogeneous and isotropic on large scales, meaning it looks the same in all directions. This uniformity is a key prediction of the Big Bang theory. However, the universe is not perfectly uniform. Small fluctuations in the density of matter in the early universe led to the formation of the large-scale structures we see today. These fluctuations were amplified by gravity, leading to the formation of stars, galaxies, and clusters of galaxies. Another important aspect of the Big Bang theory is the concept of cosmic inflation. Inflation is a period of extremely rapid expansion that occurred in the first fraction of a second after the Big Bang. During inflation, the universe expanded exponentially, smoothing out any irregularities and setting the stage for the large-scale structure we observe today. Inflation also explains why the universe appears to be flat, and why regions of the universe that are far apart have similar properties. One of the most intriguing questions in cosmology is the ultimate fate of the universe. Will it continue to expand forever, or will it eventually collapse back in on itself? Observations of distant supernovae and the CMB suggest that the universe is not only expanding, but that the rate of expansion is accelerating. This acceleration is attributed to a mysterious form of energy known as dark energy, which makes up about 70% of the total energy content of the universe. Dark energy is one of the biggest mysteries in modern physics. We don't know what it is or how it works, but its effects are observable. It acts as a repulsive force, counteracting the attractive force of gravity and causing the expansion of the universe to accelerate. If this acceleration continues, the universe will keep expanding forever, eventually becoming cold and dark as stars burn out and galaxies drift apart. In addition to dark energy, there is another mysterious component of the universe known as dark matter. Unlike dark energy, dark matter does not emit, absorb, or reflect light, making it invisible to our telescopes. However, its presence can be inferred from its gravitational effects on visible matter. Dark matter makes up about 27% of the universe, and it plays a crucial role in the formation and evolution of galaxies. The remaining 5% of the universe is made up of ordinary matter, the stuff that makes up stars, planets, and everything we can see and touch. This ordinary matter is composed of atoms, which in turn are made up of protons, neutrons, and electrons. The study of these fundamental particles and the forces that govern their interactions is the domain of particle physics. Particle physics has provided us with a deeper understanding of the early universe and the processes that occurred during the Big Bang. Experiments at particle accelerators, such as the Large Hadron Collider, have recreated conditions similar to those just after the Big Bang, allowing scientists to study the fundamental particles and forces that shaped our universe. One of the key discoveries in particle physics is the Higgs boson, a particle that gives other particles mass. The discovery of the Higgs boson in 2012 confirmed a crucial part of the standard model of particle physics and provided insights into the mechanisms that gave rise to the mass of particles in the early universe. The Big Bang theory has come a long way since it was first proposed in the early 20th century. It has been supported by a wealth of observational evidence, from the expansion of the universe to the CMB and the abundance of light elements. However, there are still many unanswered questions, and the study of the universe's origins and evolution is an ongoing and exciting field of research. In summary, the Big Bang marks the beginning of our universe, setting in motion a series of events that led to the formation of stars, galaxies, and ultimately, life. From the initial singularity to the present day, the universe has undergone a remarkable transformation driven by the fundamental forces of nature. As we continue to explore the cosmos, we are sure to uncover even more about the origins and fate of our universe, deepening our understanding of the cosmos and our place within it. Thanks for joining us today, and don't forget to like, subscribe, and hit the bell icon to stay updated on all things space and science. Until next time, keep looking up.